Today is the 5th. 5, 3, 5, 3, and this is 1325 to 1410. And yeah, there's a couple of you there. Hey, Teresa's there. Good morning, Teresa. No, good afternoon, Teresa. Soupy. That is great. And Ellie, hello, Ellie. Glad you're there. Good, and it looks like I got one more ready. So is it Anne Sophie or Zach? Let's find out. Drum roll, please. Hey, Zach. Hello, Zach. Glad to have you there. And I get to see all of you on Tuesday, okay? Which is pretty cool. A live class. Crazy, huh? You gonna know how to handle that? Since there's only 4 of you, at least it won't be so stressful in my class, right? So Tuesday, we'll kind of see where we're at and go a little further in waves and light. And then Thursday, we'll have a lab, like a live lab where you actually do something. And then I'll have time to like do it all up there in the lab, huh? Pretty exciting. My only problem is I got to figure out what lab, because you got so many cool labs what we could do that we couldn't do in the last month, 2, 3 months. Yeah, anyway. Okay, Anne Sophie, are you out there yet? If you are, say hello. And if not, I'll just pause and put that off to the side and raise my worksheet on earthquakes and ask you, do you have any earthquake tremors? Anything you want to ask about on the earthquake sheet, A through F, that you didn't understand? Now's the time, because I think it's due this afternoon at like 4 o'clock. So this would be a great time to ask. Is it okay, or you got questions? Waiting for a little response. Maybe each of you could put okay or questions. Okay, for Ellie, it's okay. How about Zach and Teresa? Okay or questions? And in the meanwhile, while you're doing that, I'm going to get to a spot where I know we need to be today. Zach says it's okay. I might have a question if you, okay. Look back, Teresa, and let me know if you have a question. I'll go on a little bit, but we'll come back to any questions that Teresa might have in just a moment. We're going to talk a little bit about light today, okay? Before we really change gears, well, not in a complete way, but we're going to talk about color today is what I meant to say. Maybe E. Okay, let's take a look at E briefly. I'll read it in case you don't have your assignment with you. It's okay, you probably have it online. It says, for tall buildings, the period of their swaying, right, increases at a rate of 0.1 seconds per story. If the earthquake waves have frequencies between 0.8 and 1 hertz, calculate the periods of the earthquake waves and the height of the buildings in stories that would be most in danger. Okay, let's do this then briefly. So the main equation we need for this, Teresa, is what? I need to get I have the frequencies. So frequencies are 0.8 hertz and 1 hertz. And I need the periods, which is capital T. So my question to Teresa and everybody is, what's the equation that relates period to frequency? You can try and punch it out either way on the screen. And best is if you can solve it for period. What is that equation for period that has to do with the frequency? How does period relate to frequency? It's been, I guess, a couple of weeks, but you might still know it. Going once, going twice. All right. Period is equal to 1 over the frequency. Ah, Teresa, you had it yourself. Okay, see, there you go. So 1 over the frequency. So what that means, Teresa, is I got to do this formula 2 times, right? Once with 0.8 hertz and one with 1 hertz. Now, I'm going to do the 1 hertz one because the number's easier. And Teresa, you can do the 0.8 hertz on your own. It goes like this. For the 1 hertz, it's going to be 1 over 1 hertz. Well, we know what that is, which equals 1 second. Okay, 1 over 1 is 1. We know that. And then it's okay. And then, Teresa, you'll have to do it again for 0.8 hertz because you need like a range of values. So 1 second to blah, blah seconds. Now, notice that it's 0.1 seconds per story. So I'm sure you can do this mentally, Teresa. So if it's 0.1 seconds per story and I got 1 second, then of course, so it'd be 10 stories high. And I'll let you do the other one with the 0.8 hertz and then work that one through. So to make a long story short, you don't want to have your building that's 10 stories high or whatever stories to the other answer. So there's a range of values you won't want, but definitely 10 stories you want to avoid because that would be the one that would resonate and potentially make the building fall over. Okay, you wrote never mind. Teresa, is that okay now? Can you finish up the rest? Is all okay? And also everybody else, anybody else got a question about Zach? Are you okay with it? And Anne-Sophie, I don't see. Oh, that's right. She can't be here. She's got some kind of appointment. So she'll have to watch the video. All right. Are we good? Anything else? And then I think, Teresa, you'll be able to do F then too. Then that should be pretty straightforward. All right. Are we okay with earthquakes? Okay. All right. Good. Then let's continue with color. We started a little color yesterday, and I wanted to talk about color a bit. Color has 2 theories. It's good. Thank you, Zach. Okay. Color has 2 theories. I'll just write that. Color. 2 theories. And they're pretty good theories. This is more or less how we think of color. Okay. The main one you and I have been using so far is called the subtraction theory. All right, the subtraction theory is that white light, first off, white light is a mix of what? Some of you might know this already. White light is a mix of what? And we're talking about only visible light, okay? So white light is a mix of, maybe 2 blanks. What do you think? Hint, if I take a prism, which I could do in class if I was in class, I can divide the white light up. So white light is a mix of, thank you, Ellie, all colors. Okay, so let's change to blue because I'm wearing a blue shirt, which I think you can see. My undershirt is blue. So as an example, if I take white minus whatever colors, equals blue. We'll fill in the whatever colors in a second, okay? We'll come back to this. I kind of did it in a bad order, but it's okay. We'll fill in the blank in a little bit. You know what I mean? So it's like white light is coming from either the sun or your lamp in your room. And if I take out some other stuff, blue is what's remaining. So blue is re-emitted to you. We had that word last time, right? Re-emitted. So the little pigments in my blue t-shirt are going to be re-emitted and come back to you. Okay, turns out the white light or the subtraction theory is based on the idea that I have three primary colors that make up white light. So it's sort of like this. White light equals, and I want to do this carefully because there's two theories. And I'm going to screw this up if I don't read it carefully, because it's not the same for the other theory. There they are. Okay, so it's yellow, cyan, which is like blue-green, blue-green, and the third one is magenta, which is like blue-red. Magenta. So here's what that means. Here's what that means. To get the color of my shirt, we got to subtract out all the rest. So look at that. I got more or less cyan coming at you. So I got to take away yellow and magenta. It's not perfect because my shirt's pretty much just blue, but let's pretend that it's cyan in color, okay? So that I take away those two, I get blue if I take that away from white. So that's what I mean by the subtraction theory. And the idea is really coming back to molecules. Okay, so the idea is pigments absorb or subtract out the molecules and then re-emit what is not subtracted away. So molecules absorb some light, and that's the subtraction part. I think last time we talked about chlorophyll, right? It absorbs all the light except for green, and re-emits the rest. I know that's a little repetitive, so I'll just not spend any more time on it than that. That's probably plenty. Hopefully you can see all that okay. All right, that's the one theory, and that's kind of the one we've had so far as subtraction. It has also to do with paints, right? Or if you were like me and when you were young, you had little crayons. Do you remember making like orange crayon by doing yellow and red crayon. So I did yellow and red, and then the orange, turns out it absorbs both of those, yellow and, no, other way around. The orange absorbs all the other stuff and then gives back yellow and red light, which is what we see, re-emits that. Same with paint. I can mix paint, right? I can mix red and blue paint, and so those will be mixed together, and then it'll absorb a lot, okay, and just re-emit the purple color, okay. So if I mix lots and lots of colors, I tend to get a dark brown, which is close to black, and it's absorbing everything, okay. If I have lots and lots of types of paint that I put together, don't do that, it doesn't look good. We tried it once in college. Okay, we'll just mix everything. It's kind of ugly. All right, let's talk about the addition theory, okay? And it's exactly that. Colors add up. Let me do this smarter this time. Let me give you the three primary colors for the addition theory. And I'll explain where you might have had experience with this already. So three primary colors for the addition theory are red, green, and blue. Which used to be the color of little pixels on old TVs. And so you could get all colors with those three colors. Okay, what's the application here? The application here is theater lights. Remember when we used to have school plays, and I hope we will again real soon because I like them. Have any of you been at our school or another school, been in a school play? If you have, raise your hand. B, if you have they used spotlights? Because often the spotlights, if they really are a good theater, they're going to have a red one, a green one, and a blue one. Now I'm going to try and show you that. I can't really show it effectively with markers, but I'll try. Okay, let's say you're standing here. Here you are on stage, and you're doing a Shakespeare soliloquy. Let's make it this time Zach. So there's Zach brushing up his Shakespeare. Right? Juliet, thou art fairer than the sun. Blah, 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 blah. Okay. So they're shining some spotlights on him. There's my spotlights. One of them shines down green light. One of them shines down blue light. And one of them shines down red light. They'll do this by putting little gels on there. So all that comes through is green, blue, and red light. So what color is around Zach? What color is here? When they shine together, when they join, what color will that be? Maybe I can make them go a little longer so you get the idea. There's the green. There's the blue. And there's the red. So when they all join, what color will what color will be on Zach? Yeah, exactly, Zach. You know that. You've done this before. White light, yes. So all three mix. And so we say, aha. So white light on Zach. Okay? White light on Zach. Because all three add up together to make white. In fact, I can put this here. Bomb plus blah equals white. When I first saw that, I thought it was pretty weird, but it is true. When you use theater lights, it funnily enough, oddly enough, it adds all up and you see white light on the performer. That's the two theories. Good. I want to spend the rest of our time talking about where we find these theories in nature. Okay? We talked a bit about technology. Now I want to talk about nature. Where do you find this stuff outside in the real world? And to do that, we need to talk about one more type of effect. That's one of my better drawings. I'm kind of proud of that. I want to talk about one more effect with you, which is called scattering of light. I'm not talking about my scattered thoughts today. Scattering of light. So what the heck does that mean? Okay. It's talking about light hitting molecules of air. Probably we're talking sunlight, okay? Light hits molecules of air. The light is then re-emitted as blue light. In other words, the particles, think of what's in our air: argon, oxygen, carbon dioxide, neon, nitrogen, a lot of nitrogen. The molecules accept the sunlight and then they give off again light, but they don't give off the same light. They don't give off white or yellow light from the sun. They give off blue light. And that is part of the truth. Actually, you ready? This is the part I think is pretty cool. This will blow your mind. Actually, I'm going to erase my theater diagram, even though I like it. Mostly violet, not violent, but violet light is given off by scattering. By the way, the light is scattered in all directions. I guess I should have said that. That's why it's called scattering. So think of sun. Sun comes down and it hits some molecules. And the molecules then absorb some of that light and give it off as violet light in every direction. Violet is the most common light given off by these particles. The second most common is blue. You ready? Humans don't see violet very well, but we see blue very well. What does that mean? It means This is why the sky is blue. Isn't that bizarre? So to be honest, the sky is really more violet in color, but our eyes are not designed to see that very well. Cool, huh? So that's why the sky is blue, at least to you and I. So it's the scattering of light, absorption by molecules in the atmosphere. What about the sky color on the moon? So I'm going to have you take a mental trip. Ready? Okay, you're standing on the surface of the moon. You're looking up. What's the color of the sky on the moon? You might have seen this in pictures anyway. Somebody type it in. So the color of the sky on the moon is what? So what's the color of the sky if you're standing on the moon? Yeah, right. Good, Zach. It is. It's black because the moon has no. So last blank to fill in here. Why? Because the moon has no what? Thank you very much, Ellie. No atmosphere. No molecules of light to catch the sun and resend it back as blue. Can't do it. They're not there. So on the moon, other than the stars and the earth shining, it's just a black sky. So see what I mean about natural phenomena? I think this is cool. That's why I like to talk to students about this. I think it's cool to know why the light looks like this at different points of the universe or of our Earth sky here as well. Let's do another one. So that's like a blue sunny day like we had today. I don't know if it's still nice out there. It was. Let's talk about a cloudy day, what we've had so many of lately. Cloudy? Why is it then white? Or gray white, depending on how many clouds there are. Well, it turns out the particles in the clouds, the water droplets, really vary in size. So water droplets vary in size and the scattered light from those droplets, scattered light is given off in many frequencies. And these add together, remember the addition theory, these add together and we see white. So a cloud looks white. I'll write these add together and make white clouds. Let me reread that, make sure it makes sense to you. So water droplets vary in size and the scattered light is given off in many frequencies. These add together and make, white clouds. That's not so fun. We're going to talk about something funner, and that is sunsets or sunrises. Why are they red, orange? I don't know, maybe yellow. Well, it turns out all these colors are pretty low frequencies. And low frequencies, just like sound. Remember when we talked about sound and low frequencies carry further? So you can hear somebody's bass from the car from really far away. Low frequencies of sound carry further. Low frequencies of light carry further as well. So it turns out these colors, red, orange, and yellow, are low frequency. So they scatter the least. At dawn and dusk, so sunset or sunrise, at dawn and dusk, the high frequency lights like blue and purple and green are all like filtered out. They're all scattered out, and only the low frequencies are left. So high frequency blue, green are all scattered out. In this case, scattered means a slightly different thing. They're like taken out of commission. And why that happens then, it's because if I got sunset, here you are. If I got sunset, the sun has to go through quite a bit more atmosphere to get to you. At midday, when the sun's above you, there's a lot less atmosphere it has to travel through. But at sunset time, it's going through a lot of atmosphere. So a lot of this is gone at dawn and dusk. Okay? I'll just write here, more atmosphere to go through. How about travel through? That's a nice word. Remember when we used to travel? So the light comes in, I see the sun over there, looks beautiful, and all the blue and green and whatever violet light is all gone. It's scattered, it's absorbed by the molecules of the atmosphere. What gets to my eyes are the colors that are a low frequency, red, orange, yellow, and those are the ones I see in the sunset. So if someone is standing over here with the sun right above them, they don't see that set of colors, right? Weird to think about. They're looking at the same sun and they're not seeing that same set of colors that you are, right? Maybe you're watching sunset and somebody in Shanghai is seeing the same sun, but it's more overhead, so they're seeing just the normal blue of the sky. Yeah. So that's sunsets. Yeah, we're doing okay. All right. Then last color effect I want to talk about is when we look into water, especially like seawater. Turns out, and you might know this as a diver, have any of you done scuba diving? If you have, as I go down 5 or 10 meters, what color disappears? Let's see if some years I have somebody who's done scuba diving. So Zach, Teresa, Ellie, maybe you know this anyway, but as I go down scuba diving, what color is lost after 5 or 10 meter depth? Because it turns out the water absorbs this color. Anybody know? I'm guessing the answer is no, but I'll write slowly here. Water absorbs red. Here, let's write red and red. That would be a smart teacher. Writing red and blue would be sort of stupid. How about that? Okay. So water absorbs red wavelength. That's the little wavelength symbol, okay? Everybody see that all right? Not sure you can. Yeah, red was a good guess. And Teresa knew that too, right? Okay, so red is absorbed. So now it's talking about the subtraction theory. So we got white minus red equals blue-green. So we get a blue-green C, don't we? I'll at least underline it in blue and green. So if the water ever looks blue-green to you when you're traveling, that's why. The red has been absorbed by the sea, by the seawater. Ute. Okay. This will be the next little item, a little review, Ellie, perhaps for you, because I think we talked about this in AP Chemistry. And that is, have any of you seen, so I'll ask Teresa, well, I'll ask all of you, have any of you seen the Northern Lights or Southern Lights? The Northern or Southern Lights. Have you ever seen any of those? Sometimes they just look white, and sometimes you see colors like reds or greens or blues. Ah, Teresa's seen them. Oh, cool. Lucky you. I saw them in Montana, but it's been a long time ago. In Norway, great place to see them. Norway, Iceland. If you get up there, not in the summer, but at other times of year, you may well see them. Nice. Oh, are you lucky? Okay, well, you might know this already, Teresa. I don't know. But the reason has to do with what's called line spectrum. And again, Ellie, we had this in AP, so bear with me. And it means that each element when hit with energy, with, let's just call it light, gives off only specific colors. I'm trying to think how I can do this for everybody. When hit with light gives off specific colors, I'll write here due to electrons. I think I'm going to show you this because it's cool and it'll be good review here. Anyway, so here's an atom. Here's the nucleus. Remember, that's in the middle. And let's say it's got an electron. Let's just make it 1, E minus for electron. And turns out if it gets hit by light, the electron jumps up to a new level, a new shell, we could say, right? But it doesn't stay there. And as it drops back down to where it came from, called the ground state, this is called the excited state, it gives off light. And every element gives off different colors because it has different number of electrons and different number of protons. And so every element has a unique line spectrum. So electrons drop in energy and give off colors or color. Every element has a unique line spectrum. That's going to be important here for northern lights. So like carbon is different than oxygen, then different than nitrogen. You can guess where I'm going, right? Because some of those are in the Earth's atmosphere. So every element has a unique line, just means lines of light, okay? And spectrum is like like a rainbow. So lines of light from the electrons jumping around when they're hit by light. And this is probably what Teresa then saw, whether you realized it or not, Teresa. So kind of goes like this. For northern lights or southern lights, if you're down in Australia, northern lights, it's from the sun that's really causing this. So solar winds send light or sometimes even ions. It doesn't matter for us. And these hit molecules in our atmosphere. I hope you can read that. My blue's getting faint again. Why does it keep doing that? Let me read that off here. Yeah, that's hard to see. Okay, so northern lights. Solar winds send light or ions, and these hit molecules in the Earth's atmosphere. We're talking like, I don't know, O2, N2, and so on. O2, N2, blah, 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 argon, whatever. And each element gives off different colors. Now, Teresa, when I've seen this, I've only seen white, and white is like a mix of colors. So it's lots of elements absorbing energy from the sun and giving off light, and I saw it as white light. It was still cool, but my question to Teresa is, did you see it as white or did you see colors like red or green or blue? Because if you saw colors, then you saw, like, I'm going to make this up, all right? If it was O2, maybe it was just the O2s getting hit. that were absorbing a certain wavelength and they gave off green color. Or the N2s might be giving off some blue color if they were getting hit by these particles. So, Teresa, did you see colors or just white? I would like to see colors, but I've only seen white in Montana. Okay. All right. No notice from Teresa, but there might be a big lag here. She saw colors. Okay, so Teresa, you saw certain atoms, like either oxygens or nitrogens, those were absorbing the energy from the sun. And when they re-emitted a color, it was a fairly pure color because it was just the oxygens giving it off, like green or blue or whatever. You're a lucky person. I hope I see some colors someday. Okay, my people, the next time I see you, I will really see you. So I wish you a good long weekend, okay? Keep the faith, all right? We're going to be together next week. See you with my mask on. Stay healthy until then, okay? All right. Bye-bye.